Alright, locate your notes, local maximums and local minimums. Functions have hills and valleys, places where they reach a maximum or minimum value. The plural of minimum is minima. The plural of maximum is maxima. Together they are called extrema. A turning point may not be the min or max for the whole function, but locally it is. We're going to find these local minimum and maximum values using either the graphing calculator or Desmos. When it's not the absolute minimum maximum, it's called a relative maximum, like here, or a relative minimum, like there. Alright, look at example 1. We're asked for the least degree. The least degree is how many real zeros there are. There could be imaginary ones that we can't see. So we're looking at, for the least degree, how many times it touches the x-axis. So we've got 1, 2, 3, 4. So our least degree is 4. Alright, lead coefficient. That's our A. What is A equal to? Alright, whether it's positive or negative. When we look at the right-hand side of our graph, since A is going up on the right-hand side, as x increases, y is increasing, it's telling us that our A is positive. And in this case, we're keeping our A to be 1. Alright, our zeros. Every time it touches the x-axis. So at -3, -2, -1, and then again at 1. Alright, let's turn these into factors. So if x equals -3, the factor is x plus 3, x plus 2, x plus 1, and then x minus 1. Now to make this equation, we can either leave it in intercept form, here remember I told you our A is 1, or we can multiply it out and put it in standard form. Alright, the extrema, the local maxima. So we want everywhere we have the highest peak. So here and here are our local maxima. Now to find these, we have to use our calculator to get the coordinates. And we can estimate them from our graph on this one, but to actually find what they are exactly, we're going to need to type this into Desmos. So let's open Desmos, and we're going to type in the equation. Y equals x parenthesis x plus 3 x plus 2 x plus 1, and finally x minus 1. And we should have the exact same equation that we had before. Alright, so I'm just going to pinch it a bit so I can see. Alright, so you see that here's the coordinates that I need. So negative 2.61. So these are the following coordinates that I need. Okay, so I want the maximum. Now we always do this in terms of our y value here. So our local maximum, this one of them is the 0.941, and alright, and then we have local minimums at negative 1.383, and the other one at negative 6.914. Alright, now decreasing and increasing intervals we do in terms of x. Alright, so an increasing interval we're going up here, and then again at the end. So an increasing interval, remember we're always open and we're in terms of x. So negative 2.61 to negative 4.47, and then 0.33 to infinity. Our decreasing intervals, so decreasing, is from negative infinity to negative 2.61, and from negative 4.7 to 0.33. Alright, domain is all reals. And a range, we bottom out at negative 6.914, and we go up to infinity. Alright, look at this example. Alright, least degree. How many times does it touch the x-axis? We're doing 1, 2, 3, 4, 5. So our least degree is 5. Our right-hand side of our graph is up, so that means our lead coefficient is positive. Alright, local maximums. So we're here, our maximum here and here. Alright, so our local maximum is 5 and 3.9. And our local minimums, we're low here and low here. So we're at negative 3.3 and negative 2.5. Alright, increasing intervals. We're increasing in terms of x. So negative infinity to negative 8, negative 2.5 to 2.2, and then finally 5 to infinity. Decreasing interval. So decreasing. So what is that? Negative 8 to negative 2.5, and 2.2 to 5. Alright, our domain here again, our domain is all reals. And a range, it's going to be all reals too.